And after the talk, we will also do a Q&A session. Yeah, let's start it.
Okay, so this is the, oh hi. There's a lot more people here than I expected for a talk that wasn't scheduled 24 hours ago. So this is the emergency backup talk for CCC. See? And it's a bit rough. I was actually still writing it on this stage 5 minutes ago. So there's some slides that I really wanted to have in here that aren't because I couldn't find the file to cut and paste the stuff from. So I'll just describe it in words. But this is basically a bunch of bits and pieces of some other research I did, and so at least that part was done. I always say, oh, next year I'll have my talk done by the time I'm due to give it on stage, but I don't know. So, all right. So okay. So everybody here's heard of Dooku, right? Because I don't want to explain it. Okay, good. So. Anyway, so there was this, it was the son of Stuxnet or something, and this talk is not about that. And the initial like keylogger thing that was used in the attack was originally sent to the victims in an Office document that was emailed to them, and it was an embedded font that was an exploit for an ODE in the Windows kernel. And so this was discovered around, or at least it was publicly reported around the end of last year. Crisis apparently just was the original discoverers, and then Symantec and Kaspersky did a whole ton of press releases about it. And so forth. And Kaspersky actually went back and actually found some examples of the attack as far back as 2010. So I don't know how old this exploit's been around for, but it was apparently being actively used at least 2 years ago, or at least for a year before it was discovered. And then 3 months ago, this particular exploit was in the news again because a number of Russian exploit kits have started using it. Originally, the Cool exploit kit was, and then followed up with Black Hole, except it's really hard to tell because the Cool exploit kit and the Black Hole exploit kit are almost identical, and they might actually be the same thing. There's still some debate. It's basically the admin panel is different, but otherwise everything else on the exploit kits is identical. So I don't know what's up with that. And so last night while I was Googling on this, I noticed a bunch of reports from back in June that make sense now in context. There was a Black Hole exploit kit that actually had some early alpha version with this particular font exploit on it. It was named test or whatever, and it didn't work. And so nobody really figured out what it was. But looking at the current exploit in the kit and looking at the prototype back in June, it's clearly direct code lineage. So most of the slides I wanted to stick in here were going to be up at the front. So. Because that's other background on the stuff. But the only difference so basically the only difference between the version of the exploit that was being used by Black Hole and Cool and stuff like that, and the one that was used in the Dooku attack was basically the shellcode was different. Otherwise, it is nearly bit for bit identical. Like even the metadata is still the same. Like the copyright on the font is still the same. The last timestamp for the metadata modification is all the same. The number of CVT entries is the same, and so forth. The big difference is that it was compressed into an embedded OpenType font, so you could basically drop it into a web page. And so there was like some slight changes that. Some slight transformations that happen when you go from a TrueType font to an OpenType font, but as far as I could tell, there was basically no changes other than the shellcode, and 2 bytes of the font program were nulled out. I'm not entirely certain why that is yet, but it doesn't seem to affect performance. So the shellcode in the original Dooku exploit would sleep for about 10 minutes and then install a kernel device driver that was embedded in the font, which was like a rootkit keylogger thing. I haven't actually examined that part. The shellcode that's in the exploit kit versions downloads an executable file off of the site, drops on the disk, and runs it. So here's the technical part. Well, here's a bit more background. So for some reason, Windows parses, actually does the graphics drawing for fonts inside of kernel memory, not in user space. And it seemed a bit mystifying at first, but I made a discovery last night. I was like I was poking around on Google or something, I can't remember, and on the MSDN TechNet on Microsoft's website, they actually have a document they wrote back when they made this change, explaining the rationale for it, and it's got some hilarious quotes in it here. So bear with me. So this is the actual URL to it if you want to go read the full thing. Anyway, it's basically, it goes to great lengths to argue that there's no security problems that are introduced by moving all of the font rendering code up into the kernel. It's like, yeah, the kernel mode implementations of Win32 are fully protected from direct access by applications. Right. And, oh yeah, and so processes can't write the memory locations occupied by kernel code, right? Anyway, so consequently, there's no change in stability or reliability. Or there's even more. Hang on a second. Oh yeah, so they go into like this whole marketing thing about how they're so much better than OS2 Warp. And then, and that basically, other operating systems like Warp, are not high-end platforms like Windows NT is. They're just medium-range ones, so they can actually they're okay with crashing on a bad font or something. And this is the best part. This is my favorite part. On the section on security, it says that essentially making this change won't have any effect on the DoD C2 and E3 certification on Windows. If you remember, like 10 years ago, that was a big deal that Windows had been C2 certified, which basically means that you glue the floppy drive shut and don't have a network card. But Microsoft hyped it up like crazy because they were trying to sell a bunch of stuff to government agencies. So yeah, apparently this doesn't break the certification somehow. Anyway, so all right, so TrueType fonts, they're actually little programs. So here's a bit of background or on fonts. Here's the history of fonts. So the Earth cools, and then everybody starts using bitmap fonts, and then Adobe, they come with PostScript. And they actually do proper typesetting and stuff like that, so you can actually have proportional spacing and stuff like that. And that's where all the PostScript Type 1 fonts are. And they're all done using cubic Bezier curves. Then TrueType fonts were basically created because Adobe had a patent on cubic Bezier curves, and nobody wanted to pay the license on it. So TrueType uses quadratic curves. And then OpenType is kind of similar, but with some more features. So so there's an actual virtual machine that interprets the TrueType font and essentially performs a series of a bunch of graphics operations to basically draw the outline of a character. If you want to draw a letter D, you say these are the dots and connect them like this, and and then you've got a letter D drawn. Then it rasterizes it, so you can scale it to whatever size and so forth. You should all know this. So the actual file format's actually pretty simple. It's one of those file formats where there's basically like a table of like offsets and links and checksums at the beginning, and then basically just giant chunks of structures just stacked one on top of each other. It was originally, I think it was originally developed for the Mac or something, so it's in big Indian byte order. Anyway, it looks like this. Anyway, you don't have to care about any of this stuff at the beginning. It's for doing well, actually, this is the magic number. There's actually like several possible values for it, because Apple did one thing, and then Microsoft did another thing, and then Microsoft did yet another thing, and so forth. This is for doing some sort of binary search tree thing if you can't fit an entire font into your 128K Mac. I don't think it's really used much anymore, I think, but I don't know. It's not really the interesting part. So there's basically 16 tables in this font here, and each one is 16 bytes long. So each one starts with a little tag. This one's the embedded bitmap data tag, which has that magic number. It's got a checksum, which is literally just all the bytes added together, divided by truncated at a 32-bit boundary. And this is where it starts in the file, and that's how big it is. Anyway, next one, same thing, and so forth. So in this particular font, the font program, which is this particular table entry, starts over here. Anyway, so the font program, it's a fourth style language. It's a push-down stack autonoma. If you're familiar with PostScript at all, it's basically like PostScript, but with less stuff. And so most of the opcodes are about 1 byte long, and they'll take like a 1 or 2 byte argument. So in this particular case, this font program starts here. The first instruction is a push. And there's an immediate value. It pushes a D word, so that's what the W stands for. In this particular case, it pushes this number for some reason. I haven't actually figured out why, actually, because it doesn't. This just seems to be like kind of this program just seems to be here, so that there's something here that does nothing. It's sort of a no-op, but it has to be there for the exploit to work. I'll explain later. So anyway, it pushes some more bytes, and it multiplies them together, and then it pushes another D word on, and then it adds them together, and then it sticks another 12, another value on the stack. This time it's 12. Then it adds that, and then it jumps to that address, which goes way off into the end of the program, which basically, for a TrueType font, means stop running. The program terminates when it hits the end of its little defined memory space. There's no explicit halt instruction, so. So there was actually a whole like 100 slides in here on like how to analyze this that I cut out because some of it I can't really. I don't know if I can actually talk about, but all this stuff more or less applies to the exploit kit stuff too. So anyway, so there's this glyph program. So when the crash happened, it was in the middle of this particular function call right here. If you go into like KD and look at the do analyze or whatever, it'll say, oh, this is the last function on the that was called. And so something in here, whatever. So basically, this is something in this function eventually led to executing shellcode. And the last thing this thing was looking at its arguments were basically this font program here. So it's pretty easy to read. This is the length. It's another thing. It pushes some more zeros on. It stores them in an array. Flips a bit for whether or not to mirror your images around the x-axis. Sticks another zero on the stack, and so on and so on and so forth. And I'll explain what that all means later, because that's the important part, actually. This is the important part of the exploit. So if you're in a kernel debugger, it looks like this. This is the stack. These are the stack frames that are still intact, at least at the time the system blue screens. So the particular font that I'm using to induce this blue screen of death crash has the shellcode replaced with a call instruction that calls back to itself. So it just fills up the stack and then crashes when it hits the end of that stack frame or that page. So pretty much these are the functions, return addresses, so on and so forth. This is the first argument, second argument, so forth. If you take a look at it, yep, that's the font program we're just looking at, indeed. Yeah, that's it. So the second argument points to the end. These are the flags, which is, that many bytes, it's pretty much that value plus the length of the thing. So it's basically pointing at the end. Anyway, which is kind of right there. Here's a reminder. Yeah, this is what I just said. So yeah, the weird thing about this though is this flag fields. It's in this particular table there's another 4 bytes at the end for some flag settings that aren't actually used by this at all. And so it's curious that whoever created this font set the value of these flags to 3137 in hexadecimal, because it doesn't actually make any sense interpreted as flags. And I'm like, what could this possibly mean? Anyway, interpreted as flags, that's what it means, which doesn't mean anything. It also doesn't quite make sense because when you first look at it, you think, well, it'd be like 31337. No, wait, that doesn't work because they're backwards. So I don't know what's up with that. If anybody has any ideas.
Somebody gets confused from the idealness.
Yeah. So that may very well be the reason, actually. The comment was somebody got confused by the endedness. So anyway, there's the return address. If you go and look at it, it's trying to move, or rather, there's the call to the function where the shellcode happened, and then a fault happened. It never actually made it to that address. It was supposed to return there, but it never actually did. So somewhere down this path goes to shellcode. Anyway. There was a whole sort of narrative story that went along with these slides of like, here's how you would analyze a kernel exploit if you suddenly have to analyze a kernel exploit like this. But I'm just sort of skimming over it because I just kind of giving you the important stuff. So there's this other argument also that was whatever the current offset was for. Oh no, this goes to the global VM state structure. So I'll go into this in a moment. It's very obvious it stores whatever this thing is. It points to a bunch of more pointers, and then ADI is of course the index. Is apparently it's pointing to almost to the last instruction, but not quite. So it was the index counter, I'm pretty sure, for like what the current instruction is while walking down this thing. And so the funny thing is that the last instruction that was executed therefore must have been this some storage word or something. No, or whatever it was an LSW in the actual documentation for true type fonts that I'll explain later. There's a slide for that. So the last instruction it called was that, and then it crashed. And so it never actually got to execute any of these. And this is significant. And I'll explain this mystery in a moment as well. So, and so the Stack Overflow, that's the stack. You see it's full of zeros. It's got a bunch of zeros at the end because it got overflowed. That was what the actual blue screen was. Anyway, the other thing was if you're trying to figure out how to get from here to this pointer that points to the shellcode, there's a distance. You can figure out the difference between each of the registers and where this particular pointer to the shellcode is. In this particular case, it's which one is that? It's ESI plus 80 bytes, say, for example. But it could also be EAX plus whatever that is, 172 bytes, or possibly EBX plus 4 bytes, and so on. If you're in a hurry and trying to figure out which instructions to look at first. So pretty much at this point, I basically went and started reverse and win32k.sys to figure out, well, what was actually going on in the code. So that was the instruction that died. Or there was the last call. This is what it looks like in IDA. And by the way, there's a thing, when you pull this thing up and you look at it, there's something you'll immediately notice in the function name list here, that the names of all the functions are the exact same ones that are in the documentation, like the Microsoft and Apple specification for TrueType fonts. So it's hey, this is an instruction implementation. It's a big jump table. So yeah, I mean, if you go and look at it, this is the not opcode. And you go down this branch, and it does a not or whatever. You go down that branch, and it doesn't. You do neg here, you go down this branch, you negate whatever that thing is, and otherwise you go down this branch. This is, hey, there was an error generally, as a not equal to, and so forth. This one is multiply, so it does some stuff, and then it goes down this way, and it calls this function, which actually does the multiplication, because it's this weird floating point format. So they use this weird, they don't use standard IEEE floating point. They have their own special floating point format in TrueType fonts. It's, I'm trying to think, it was something like a 26-bit base part, and then whatever it was, 6 bits of exponent or something. It's basically 32 bits in actual memory. So you don't actually have to care about that for writing kernel exploit. Here, I'll explain. So there's this big jump table of all the instructions. Each of these offsets is 4 times the opcode value. So it's pretty obvious what this does. Anyway, this is the virtual machine basically does the decoding and then calls each of these functions and so forth. Yeah, there's 190 of these. So they also all take the, if you actually look at, so the other thing is if you look up, so IDA has this, if you've ever used IDA before, it's got this really cool feature to say, hey, tell me everything that references this memory or whatever. You can do, essentially, it'll give you all the back references to figure out what calls here or what uses this, which is really, really useful for tracing things backwards and stuff like that. So this particular dword variable is used by all this stuff, like all of them. And this particular one is always set to these values here. So there's probably some sort of error code. Particularly because this is always used when it goes down the branch, so it doesn't actually do the thing the instructions, the opcode is supposed to do. So, like here, for example. And then and so forth. This one too, there's like 200 of those. Whereas if you look at some of these other ones, this particular dword only shows up like 11 times. And it's all in like call, loop call, and various looping instructions. So it must have something to do with some sort of loop counter thingy. This one is a jump. This one only shows up in jump instructions, so it must have something to do with maintaining jump state. This particular one only seems to be used by if-then statements and loops. So some sort of conditional thing, whatever. Anyway, there's a couple of symbols they left in the public symbols that you can download off of MSDN. One of the symbols that was left in was local GS. So I'm going to speculate that there's probably a global GS somewhere else in here. Particularly because there's a function called update global GS, which takes that particular D word I was pointing out earlier as the argument. So anyway, several hours pass, and you go down the code, you get to there, and then you go down somewhere here. Hang on a second. So somewhere down in here, there's got to be a call or jump that goes to the shellcode. Logically, it has to be somewhere in this function. So here's the main loop of the interpreter. You can see it basically grabs a grabs a byte, and then basically looks it up in the function table, takes whatever that value is, multiplies it by 4, that's the offset, and then it goes and it runs it on one of these branches. Hold on a second. Oh, no, actually, it follows through to the other one up here. But anyway, this is the lookup. So, and so on and so on and so forth. So most of reverse engineering is basically just doing this for hours. It's not actually that hard. It's just a lot of this. A lot of people ask me, Bryce, like, how do I get started in reverse engineering stuff? And I'm like, it's not actually that hard, really. It's just a lot of simple stuff. Lots and lots and lots and lots and lots and lots of it. I mean, the analogy I use is like solving a crossword puzzle. A crossword puzzle this big is not too hard. But if you make it like 10,000 columns wide, it doesn't really get any harder. It's just bigger. But anyway, so digging through a bunch of public documentation on stuff. There's some important to know opcodes, which are actually used in the exploit. And this one, this is one of the important ones, because it's basically what's actually used for writing stuff onto memory, into kernel memory. Because it basically, so the internal, I probably should make a slide for this. So the universe, if you're a true type font program, your view of the universe is you've got like you've got 4 data structures that are available to you. There's the stack, and all of the operators grab their arguments off the stack and put the results back on the stack. Then there's a storage array where if you say, oh, I want to put this somewhere other than the stack, you say, okay, just stick it in this array at this offset. And then there's the CVT, which is a control value table array, which is basically a similar sort of thing, except it's for the actual points that are used for drawing the outline on the font. And then there was one other array, but it's not. It's another array. I think it has another specialized use, which I've forgotten now. But it's you can look at the documentation for it. I guess it's up on Microsoft's website. So I was saying, this is the funny floating point thing right here, which is actually 32 bits in reality. But if you're actually trying to draw a font, it'll be this floating point thing. So so this is global graphic state. And then there's also this, so the first thing basically points, so here's the 3 data structures I just told you about. So this first pointer, points to the beginning, the bottom of the stack. Every time you put something on the stack, this goes up or down by 4. This points to the storage area, which was the put whatever you want in here array. And then this points to goes to the control value table. Which is for the points for the outline. If you notice, well, I have another slide that draws more attention to it, but if you notice this particular value happens to live like right before this one in memory, by about 4 bytes. Here, let me skip ahead a bit. Well, so the other things in here, like this is the number of pixels and the thing. When I did this, triggered this particular crash, I set the font size to 4 points because I didn't know if it mattered. And so forth, and then stuff. There's a pointer to shellcode, by the way. So you go about 134 bytes from here, and there's this, which is the length of the CVT array. In this particular case, it's 129. And then there's some other stuff that doesn't really matter. And then I think that's the end, I'm not entirely certain, but I think it is. And then, but the thing is that I highlighted this because this right here is the important part, because this is what actually makes the whole exploit work. So this is the good part. So the way that the exploit actually works, or the way the vulnerability actually works, hang on, is you're merging, there's 2 bitmaps, because TrueType also supports bitmap fonts in addition to outline fonts at the same time. So if you've got 2 bitmap glyphs, and you put them next to each other, and there's a pair of numbers to specify the x and y offset for where to merge them together if you're kerning them, but there isn't a bounds check on the y value. So you can say, oh, take this second bitmap and merge it on top of this the first one 500 bytes further back in memory than the end of the buffer. And but since it's a graphics addition, bitwise addition type of thing, you can only add bits to memory. You can't take them away. So the person who implemented this, they chose to write 1 single bit to memory. And there was this bit right here. They basically they added 128 to 1, so that this array was now 129 bytes long. This was the 1 bit they chose to overwrite. And what this allows to happen, and I've got a slide, I should probably just go to that slide. So the CVT value, this is at the time this happens, it's pointing to like right before this structure in memory here. And the length of it is 1 dword long originally. When you add, when you add 128 to it, this array is now 129 dwords long, but it still lives in the same place in front of the global VM state structure. So that makes this entire global VM state structure appear inside the CVT table, inside of the TrueType virtual machine, which is now accessible from the font program. So I should probably move these to the beginning of the slide deck, but like I said, it's a bit rough. I was just writing this. So the actual bug is in the if you do like a patch diff, it's in the get bitmap function for just type 8 and type 9 bitmaps or something. Anyway, it basically takes a number of rows and a y offset for the merging, and then ORs them together. And it's basically what I just told you a minute ago. This is the actual vulnerable code right here. This value comes from the TrueType font, and then this value, which is where you're writing this value to, also comes from the font. And so you can essentially control a memory write to an arbitrary location. So, like I said, they decided, whoever did this decided to add 128 to the CVT. And blah, 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 I just said this. So so I think like Microsoft like never touched ever any of the TrueType code ever. Because looking around online at like open source TrueType stuff, basically all of it was written like in 1988 and like last revised in 1993, and like nobody's touched it since. So I think all of the structures, I haven't actually looked at all the kernels to actually verify this, but I think like all the structures are all the same size, so all the offsets are always the same, and they're all relative. So you only need one offset to work on all versions of Windows, and since the kernel already knows where everything is, ALSR address space layout randomization doesn't make the slightest bit of difference because the exploit doesn't need to know where anything is. It probably goes back, I don't know if it goes back to NT3, but it wasn't in the kernel until NT4, so at least NT3.5 is not vulnerable in the kernel. Anyway, I think we established that at the beginning of the talk. So anyway, so basically, since it's an embedded font, since it's actually in the font rendering engine in the kernel, the exploit works anywhere you can put a font in Windows. So all Office documents, all PDF documents, all web pages with embedded OpenType font. There was EOT fonts, actually. But yeah, this is what's actually being used by the Blackwell exploit kit and so forth these days. And the other thing is, since it takes place up in the kernel and not in user space, you can escape from user space sandboxes around Office and Adobe Acrobat and stuff. Yeah, when I figured this out, I was like, wow, this is a pretty amazing exploit. It basically works completely reliably everywhere on all versions of Windows. There's actually a 64-bit version. So this is the 32-bit version. Apparently, there's actually I actually really deeply analyzed the 32-bit version because I didn't realize there was a 64-bit version until I saw the black hole exploit kit had a 64-bit version, and I haven't actually fully analyzed that one yet either. But it has another slightly different font program, and some of the offsets are slightly different. So other stuff. So anyway, one of the first things Kaspersky pointed out back when this was big news, and is dead obvious when you look at this thing and look at the strings in this thing, is there's a bunch. So the names table in the font is where you put the like the copyright information and stuff in the font. And this particular font, for some reason, claims that its name is Dexter Regular. Copyright 2003 Showtime Inc., which is apparently a reference to a television show. Nobody knows why. So, and this is the vulnerable code and context. So this is there's not a check done by this point. So basically this is these are the two values, and this is the multiplication, and so that basically gives you what the offset is. So I think I had some slides for doing the math on here, but I don't know. So anyway, this particular font, so it was, I guess maybe handwritten or something, but it probably has just barely the minimum bare necessities needed to actually load and do the exploit, and then a big name table that says it's named Dexter, but. It only has 2 glyphs defined in the font. Well, it has 6, but there's actually two actual ones and then 4 null ones for some reason. So to actually trigger the exploit, you have to merge 2 characters together. And so the particular 2 characters that are defined in this font are a colon and a closed parenthesis. And in order to trigger the exploit, you have to kern the 2 characters together in exactly that order. So it looks like this in a regular font. Anyway, oh, and so yeah, this is basically, there's nothing here. This is all zeros. 0, 0, 0, 0, 0. 0, 0, 0, 0, 0, 0. The tables had to be there, but there's nothing in them. This is all 0, 0, 0, 0, 0, 0. Except that one there, that's not, or actually, wait, did I cut and paste this? Right? No, you got this. Wait, no, it's on the next slide. This one. Okay, so this is the actual memory chunk of memory that gets overwritten. So basically, it's a 1 pixel by 1 pixel bitmap, and the bitmap is basically a 1 on this edge and then zeros in the rest of the byte. So that's 80 hex, and then this is the x and the y offset, and so if you multiply these values together. You end up from that value basically gets multiplied by the width, which is up there somewhere, and I thought I actually had a slide with the number, but it's basically you multiply that times the length plus that, and that's where that byte gets ORed on top of. So okay, here's the really good part. So all right, so this is the global VM state structure. This is pointing to the bottom of the stack. You know, this is the slide I had like 50 slides back. This is the CVT, and so forth. So in the middle of this is a Boolean value for keeping track of whether it's flipping a glyph drawing around the y-axis or not. And a bunch of these are just like kind of like booleans and counters and stuff like that. And so if you do the math on this, and there was some reason why I had a slide with this math on it, if I can remember. It was oh yeah, so it was basically this offset right here is 90 hexadecimal bytes from there, or 94 bytes from there. It's the same thing. Written down numerically, it's basically 25 D words from there to there. So so I was doing this because you can figure out. Oh, so basically, you know what that is. If you can figure out that that's 90, then you go back and you look at you go back to IDA and you look up all your function implementations and you see, okay, which of these moves does anything with 90 is one of the offsets. And so there's this instruction flip on, which sets ECX, which is comes in from somewhere else, presumably points right there, and then adds 90 hex to it. So it goes right there, and then it sets it to 1. So if you actually go and look at the documentation on Apple's website, or no, I think this was like Microsoft's docs. You can see it's basically there's a Boolean value that this operation that these two operands do. So you can basically go through and figure out, like, you can actually go through and figure out what each of these where each of these variables are in the state structure. But I didn't bother doing all that. I only figured out this one because it's used by the exploit. So a little bit further past this in memory, it's a pointer, which at the time of the crash was pointing off to the shellcode. It was something else originally, but I'm looking at a memory dump from a dead system here. So after the exploit. So the yeah, see there's the shellcode, which just crashes the system. So this is useful if you're like, you know, going to just if you just need a kernel dump to do this sort of analysis. So so this pointer, it was. I remember with these slides a year ago, I knew what every one of these things was. I haven't actually given this talk for a while. This is another pointer to another structure. Oh yeah, that's why. So, I think that was the original value. Anyway, so one of the things is a weird thing in the documentation. Okay, single width value. Anyway, so both the true type documentation on MSDN and on Apple's typographer's website or whatever like that lists the name of this opcode as SSW, but actually in win32k.sys it's labeled LSW, and I don't know why, but it's the same opcode. So this is the actual code here, and if you look down here, hey, there's this thing where it loads a value 100 bytes past the end of this state structure. That's the state structure, and then it calls it. So if you go and you look 100 bytes past the end, hey, look, that's the pointer to the shellcode. This value right here, EAX is basically pointing to the CVT table. So CVT table plus AC hex is that pointer. It grabs that value and calls it. So, oh yeah, there's the shellcode. So just a reminder, this is shellcode. So here's actually what the program does. So the first few things it does is it pushes some zeros down on its stack. Then it reads it back. WS is to write to the storage array. So in this particular case, it's writing to location 0, the value 0. So it's putting a 0 in the 0th spot on there. Ding. And this particular, if you go and look at one of their tables in the font, there's 32 entries in this particular array. So only 3 of them are going to be used. So the next thing it does is it flips a bit off. It was that symmetry bit. So it basically goes and it sets this the D word or this byte at this offset to 0. And then later on it goes and it sets it back to 1 again. So between, and so that as a reminder, that's where that is. So between that and that, it basically reads whatever it just stuck in that table. Ding. And then it reads the first CVT value, which was at the beginning of the thing right before the structure. See, it was 0 in this particular case. It's that one right there. That's the first thing it reads. So it basically loads that back up into the stack. And then it that one. And then it flips the bit, and then goes and it reads the next value out of the storage array, or rather the first one back out, and stuff. So here I'll instead of going through this thing by thing, I'll explain. So basically, it's the value in the storage array is being used as a loop counter. And it increments it by 1 each time it goes through this. And then it basically also uses an offset for the CVT, and it basically walks down the CVT table 1 entry at a time, but essentially does it in between a pair of these flip-on and flip-off operations. And so it's basically flipping the bit off, reading the CVT value, flipping the bit on, reading the CVT value again, and then comparing them. If they match, well, then it goes to the next one. And if that one matches, it goes to the next one. But then if there's a difference between when it flips on and flips off, then it knows it's found that bit in memory. Because what it's doing is, it's basically doing the comparison. So if it doesn't match, it goes and it jumps to this. Otherwise, it loops back up to there. So, this is the loop. Okay. It's been like a year since I looked at these slides. So it reads the value. This is the incrementing the loop index. So it adds 1, makes a copy of it, sticks it back in, so forth. Ding. So this is the first time through. This is the next iteration. So now it's at 1. This is a bug, by the way. So what this is a boundary check to make sure it doesn't walk off the end of the table, the CVT table, if it doesn't actually find this bit. And so it should be comparing it against 80 hex, but whoever wrote this exploit wrote 80 decimal in it, which is 50 hex. They mixed up a decimal and a hex representation of the loop bound. In this particular, it doesn't actually affect the exploit because the exploit happens long before it hits the end. But it was an interesting bug I noticed. So anyway, so just some math. You can probably look at these slides later or something if they ever get published. And stuff like that to follow along. Or you can just go to some black hole web, exploit site, like get infected with capture one of the fonts and do the analysis as well. So so yeah, this is an undocumented thing. So the jump is undefined for negative values, but in the way that Microsoft implemented it, it actually works okay. So this is what this was. I actually had to go and actually read through the implementation for the jump instruction in the true type VM to make sure that negative values were okay. So as according to the official documentation, they're not. Well, it's undefined, but I didn't know if negative values would be true or false. So anyway, and I actually forgot the answer now, but it's somewhere in here. The answer's in there. So so basically it goes through the loop again and does this stuff. Anyway, so and so blah blah blah. You go along, and eventually you get to there. So what we're saying, so it's basically walking along, and then it gets to here, and then this bit goes from 0 to 1, and then 1 to 0, and so forth. It says, aha, I know where I am now. I'm 90 bytes past the end of this thing, or 25 loops through. So basically, when the array index reaches 25 hex, whatever it's 37 or whatever, which is what these two things are here, then it jumps into this chunk of code right here. And it basically goes and it grabs a value, whatever this was, 4 bytes past the end of 26, where it just was, and then sticks it back down on top of the CVT value 3 bytes after that. So basically it takes that value, which points to the beginning of the font program, way over back in the font file. It's where the shellcode was living, was in the other font program. Remember that dummy font program I was going on about at the beginning that was just a no-op that didn't do anything? All right, so basically 50 bytes after that was the actual beginning of the shellcode. This is basically the address, points to the beginning of that dummy program. And so 50 bytes on top, in addition to that is basically where the shellcode is. So that's where the flip on and flip off thing is. It grabs that value, which is the pointer to the font program, and then adds 50 to it, basically, sticks it back on top of memory. And then, let me go through I'm almost to the end. Writes it there, on top of the function pointer to the rounding function. So so basically it takes, that's basically the address for the shellcoded memory. And then it calls, the plus 50. And then it basically calls remember this dummy program? Yes, that dummy program. So there's a dummy program, and then there's a shellcode, 80 bytes after it. So then, once it's copied that there, it calls the SSW opcode, which goes and it reads this function pointer. Okay, so the way that the virtual machine in Windows is implemented, there's like 6 different rounding operators for rounding modes for true type fonts, and the way that Microsoft implemented this was they actually had 6 actual functions. And when you do the opcode to set the rounding mode, it changes a function pointer for the round operation to one of these 6 So this SSW instruction is another one of those where it's basically a function pointer to which of the several implementations of this opcode are actually going to be used right now for the current state. So when it calls it, so when you call this operation, it goes and it, hang on, it's not it. Okay, good. So then it goes, remember in here, it grabs that function pointer and then jumps to it, calls it basically. And since that value is now pointing to the shellcode, when it goes to execute this instruction, the implementation for it is now the shellcode. And ta-da, you do the math, and that writes that there, and then that does that, and then poof, ta-da. Okay, so this is it, ta-da. And so at that point, you're basically running the shellcode. All right, I'm about out of time. I think I have like a couple seconds left.
Actually, you've got 40 seconds left.
40 seconds. Okay, good. I was worried I might come in a little bit over or under.
So you made it perfect on time.
What?
You made it perfect on time.
Okay, excellent. All right.
Huge applause.
Probably. So also, if anybody has any questions, I think there's microphones is how it's done. Also, in 2 hours, I'm giving another talk in the same room, which I should also hopefully have finished being written by then.
No questions.
I was wondering, since Microsoft decided on shorthand to move quite a lot of the graphical stuff to the user space in Vista just to move it back to the kernel in Windows 7, if Windows Vista might actually be the only current system that's not vulnerable to this.
I actually don't know. I haven't actually done a full compatibility test on this. I think I did this analysis like in an old XP box because it was easy, and I had a VM laying around. So yeah, I don't know. I remember there was a blog I saw where somebody tested out which patch levels that Windows and/or IE had to be at in order to be vulnerable to this, because it was on the initial. A public discovery that Cool Exploit Kit had been using this. It was like Caffeine's blog or something like that. It was like malware don't need coffee, I think was a blogspot, I think was the blog. Whoever writes this blog basically went and installed all the different knowledge base patch level changes for Windows to figure out exactly which ones are vulnerable and which ones weren't. And there's a graph on that blog if you go look, and it might have a clue about whether or not Vista's vulnerable or not. But I haven't actually tested that myself. All right.
Thank you very much for the talk. I have to close this now.
Okay.
So give a warm applause to the speaker.